welcome to this Taiyang News Tech Table at CSPV. We want to talk today about larger wafers, and we have with us three guests in this discussion round. To my left is Holger Kühnlein. He's head of research at Rena, a German leading supplier of wet etching equipment. Then we have with us my colleague Shravan Chunduri. He's the head of technology at Taiyang News. And then we have Raimund de Munich, who's CEO of Semco SmartTech, a leading supplier of deposition equipment. So we, as Taiyang News, came recently out with a report on advanced solar module technology, and we are doing this report now for a couple of years, and thought about advanced module technologies in the past. Then I think the first thoughts you would have had are half cells, bifacial modules, glass-glass modules. But when we did it last year, so we started to stumble upon something that also deviated from normal modules, and that was actually that some modules had really high power outputs, although you would think that they shouldn't have, because they were not necessarily using some advanced module technologies. But when you looked a bit deeper into that, the reason was that they were using larger wafers. And this is today's topic. So in the last few years, actually, larger wafers have made their inroads into module making. And maybe Shravan, you first. So what was the driver actually, and how did this whole thing happen?
Yeah. So last year, when we were doing the advanced module technologies report, when I was really chatting, putting the module powers, we collect important data from almost all leading module makers, and we put them, and then we really compare and see how the power rating goes up. So really something interesting came up, like LG, they were using 161.75, which is kind of M4 in today's definition, these wafers. And then also Jinko, also they introduced a PERC module, and last year we had a cutoff of 330 watt in order to, so always when we want to put the modules in the power rating list in our report, so we always put some kind of a cutoff level. And last year this was like 330 watts, and of course, so LG got IBC and passivated contact cell technology, so that was kind of justified how they entered into that level. But even more interesting was Canadian Solar. And actually Canadian Solar did not tell us that they were using larger wafer, but later we came to know. So even with using M6 wafer, multi-crystalline technology, they were able to easily come and join in this 330 plus wattage club. So we when I was doing, then we had internal discussions. So then as we did the module ratings for this year, almost a lot of companies coming up with different modules based on different wafer sizes, and a lot of companies have really went this 340. So for this year it was the benchmark was 340, and if I remember correctly, we had 25 products from the all leading module companies which had above 340 watts. And out of this 25, 16 are using larger wafer. I mean, may not be not everything M6, but definitely not M2. So M2 kind of became a standard, and all 16 products, they were above 340 using larger wafer. So I think then I thought this might be a good indication. Of course, changing a wafer format may not be a direct increment in the module or improvement in the module, but it's kind of a trick that's really working out to have higher module power output. Then this also came from LONGi, that they introduced and they started really promoting highway this M6, and their HIMO 4, two of their HIMO 4 modules were also in this above 340 watts. And cell technology is rather simple. It's PERC, today's standard.
Okay, so that means in this module report, then the largest wafer that was used was an M6 wafer.
Yeah, I think independent from the cell technology, so not IBC and shingling. So these two module technologies are, back contact and shingling, they obviously had very high power and also very good efficiency. But bearing that, LONGi's M6 is really on the top. Okay. So when only doing the simple technology, but about 340 watts for 60 cell module.
Okay. So we have two equipment manufacturers in our round. So if we start basically with the wet etching process, which comes usually at the start in cell processing. So what does that mean, going to larger wafers?
I think for us, at the first glance, people might think from outside that it is an easy approach for the wet bench manufacturers, and for sure it was in the times when we changed from M0 to 4. Not that big thing, but already for example, consumable suppliers, carrier suppliers, they had to adapt, but this is something a straightforward job. For us, it was important when we looked to the roadmaps and realized 161 coming up, 166 discussed. Only looking on the roadmap, I personally asked myself, as I'm also responsible for the strategy inside RENA, what does it mean for our future platforms? Can we, if we change things, can we already anticipate that larger wafers coming? We of course said what is actually the base. This is the diameter of the ingot. We recalculated, and we very soon came on a point before it was announced, okay, if it goes to 300 millimeter ingots, then something even above M6 would show up. So with these considerations, we designed the texture tools with the inline tools. We thought about, if really the big wafers coming, especially for the inline tools, that maybe one lane gets reduced again, so that we are expanded our tools to run up to M6 6 lanes. And then if the wafer even become larger, we can even reduce back again on 5 lanes, what is today's standard. So for us, it was extremely important to look in advance, because chemistry, pumping devices, all what we have, cooling devices, everything has to be checked, as PV is a very, very tough business in terms of cost efficiency. We also have not so much redundancy in the equipments that you easily can adopt this additional 10–15% in area. So overall, we can handle it good, because we address things early. But in detail, if in the future this will become a mainstream, they're coming challenges up, but we can handle it.
Okay. What are the challenges on your level, Raymond?
Well, first of all, from our side, as basically process development and equipment making company for diffusion and deposition, I must say I'm finally happy that the industry is moving to a larger wafer size. It's nothing new, historically already in the pipe for quite a long time. When we look back at our back then European customers in the mid-2000s, actually early 2000s, people were already requesting wafer sizes of 8" square, and back then we were already supplying equipment for these sizes. So for us as equipment manufacturers, actually it's nothing really new, and we're kind of happy it's now really truly happening. And the main challenge is now that there's no real standard set of what is the real final wafer size. And we're kind of happy with the trend that big leading manufacturers like LONGi are now setting, and also trying to take the lead in setting the standard But historically, in PV, it's not always easy to agree on the standard in the industry. So for us, as thermal equipment manufacturer, it's challenging because we need to cover the whole road, and we need to be ready for whatever wafer size is upcoming, as Mr. Kuhlein nicely just analyzed. So it's for us basically anticipating, making sure you're right, and making sure your equipment is ready to cover basically for manufacturing the next 3, 4, 5 years. So that's a real big general development challenge. But when we look from Semco-wise, how we approach that, I mean, traditionally, when we basically look at wafers, at diffusion, for instance, wafers were processed vertically in the cassette. Then the wafer quality was getting better. Gathering was useless, so we were able to put 2 wafers together back to back. Semco was the first to go to diamond shape. We were the first back then to put 1,000 wafers back to back in the tube with back then with Q cells in Germany. But now with the additional basically technology of the diamond wire sewing coming in, it's not only the wafers getting larger, but it's also the wafers getting thinner. Yeah. So the challenge for us actually is really in 2 dimensions, and as a result, we switched all our wafer handling, first of all to Bernoulli, but also to horizontal processing. So we can basically cope with larger wafer sizes inside our reactors, which are historically already ready for 8-inch square. Yeah.
But will this trend, because I think for a while nothing happened in terms of wafer thickness, and recently we saw some movement there. Will this stop now or reverse even a little bit with a move to M6? Because I think M6 probably at whatever 140, 160 might be tough.
So when we're looking on wafer thinning, let's call it like that, and on the roadmaps, we realized also that there's stagnation, and that we discussed about the small steps, some millimeters, where it's coming from, as I said before, from the diameter of the ingot. From the wet chemical application, we definitely suffer from the bow and from certain transfer effects when we get wafers out of liquid into dryer systems or into different liquids, if we have these changes in between the baths. There we definitely would suffer a lot from that the wafer would at this stage even enlarge and would get much thinner. I think we are fine, we are prepared, but we have seen that maybe also with the automation companies, our cell customers realized that the right way is go to bigger or go to large wafers and less going thinner at this stage. Because the efforts, if you really go thin, and as Raimund said nicely, if I think back in the early years in 2000 in Europe, we already discussed all these thin wafers. We talked about 100 micron wafers. We even have seen, and I have found carriers in my laboratories with my colleagues for even M12 wafer, and they are from 2005 in these times, about 2007. And if you look onto that, I think we can cope with that, but thinner will be get a challenge, but it will be for the entire automation and a lot of processes, and I believe the cell manufacturer have realized it.
And so what thickness are we talking about? 200 microns then
No.
for M6, or what?
No, I think we can stay where we are. This is what we get from pre-sampling. We are in early contact, as you said. The wet chemical guys with the first machines are the very first in the cell manufacturing. We get it in, people want to see if we can clean, dry, texture them homogeneously. Mm-hmm. In the first instance you say no problem, but then you realize it could be certain things happening, sticking of wafers, especially if you get them out of the liquid. Things like that get checked, and if we stay with the 140 microns or 120 we've seen, we can deal with. But as closer we get into direction of 100, certain challenges coming up, I cannot mention in detail, as you might understand. Yeah.
Okay. So You mentioned also that it would be nice to see some standardization. That's what I also heard from some EPCs, end users, because of course they are really, especially if they have their own mounting equipment, they would prefer to have some standard to keep it simple for their people, and to have also the flexibility to change product suppliers. But do you see a chance? Looking at the history of standardization, which in solar was, I believe, always a bit more difficult than in semi.
Yeah, I think you already answered the question a little bit yourself. So I think it's indeed a little bit wishful thinking. But at the end now, the standard will be more formed by economy, by basically big companies driving and taking the lead, setting the standards, instead of that a committee is sitting together and trying to put a standard in paper. I think the M4 was an in-between launch, smartly done. I think by then I remember well was LONGi. I mean, we worked with a big Korean customer, having that in mass production now for over 3 years. So that has been successfully introduced for multiple cell technologies. I mean, TOPCon and back contact. So everybody now knows it's working. It can be done. The breakage yield can be managed. And from the M4 161 to the to M6 166 is a small step. So at the end, for the moment, we are seeing M6 to get a real good, to be a real good intermediate standard, and then where the wafer size is finally going to, I mean, who can say? No.
Okay, so let's maybe just talk about at the moment cost, because ultimately it's about cost reduction. So even if it means bigger modules, but in the end it's about cost reduction. So how much issues are there in terms of breakage in the steps you are working in with the bigger wafers? What are you seeing there? Or because I think probably you have already tested some companies have started mass productions also with M6.
So for our applications, the breakage is something which is dramatically reduced simply to the quality of wafers we get. If I remember back in the past, the wafer output was not such a way controlled. We had a lot of micro cracks. We had really things we only looked into and they cracked immediately in the wet bench at the first steps. So these times are long over. And if you really look into that sizes, as we said, M6 as an intermediate state at the moment, we don't see any difference. So there's nothing really challenging coming up to us. As I said before, it's more like that we have to right now deal with a variety. Once a platform is maybe sufficient for up to M6 and something else comes within the next 2-3 years and larger, even announced by others, 210 to say it in words, it is difficult to have a platform which can cover everything and is competitive in cost and performance for all of that. This is something where you get challenged as equipment manufacturer. I personally like it. We are fully in this progress, and as Raymond said, it's nothing what we as a supplier can wish. It's simply we accept it, we are completely in it, we're doing the job.
So one question, Raymond. Of course, so Semco got really the semiconductor background, and you have been in the industry from several years. This might be very easy because you also worked with someone already at M4. This is easy transformation. So can you say for the deposition equipment, not really having such a background like you, how difficult is for them to cope up? So first thing is it simply changing the carrier or tubes, or really even the deposition? Because now you are talking about a few microns, few nanometers. So the deposition quality, this film uniformity, thickness deviation, all these things. So are they really easy? Like, is this one can copy and paste, or is there some serious work that requires at the background to make a product, a production deposition equipment tool ready for M6? People who have been doing M2.
Very interesting question, and it's a very long talk for me to answer. But in generally said, I mean, what's now happening basically with PV silicon solar cell technology, for any cell technology going above 23%, I mean, everything is counting. Every detail is counting, and then specifically you can see that the challenges for the layers that are deposited are higher and higher. So process window is narrowing, and also layers are stacked. So because of that, more thin film specialists will indeed be drawn into the industry. More specialists are required in order to make sure that thin film deposition, especially when layers are getting slightly thicker, remain stress-free, yeah? Or can be balanced in the process flow. So from this point of view, yes, deposition is getting slightly more complex, but when we are comparing the PV technology with semiconductor, there's still basically a very big gap. So is the industry and the engineers that we work with, are they able to cover that job? Definitely. But one of the key things is to and this is a clear trend that we see. Step one is to handle the wafers horizontal in the reactor, so they can stress-free under the temperature, whatever deposition step you are doing, can move inside the reactor, and when basically you cool down, you can basically simply unload them. So going back to your earlier question, I mean, what issues you're facing on breakage, on yield. For the thermal process, actually, generally you don't suffer a lot from what's happening inside the reactor. The challenges are more is how you're handling the automation before and after. So breakage, not so much an issue as Skulan just said. We don't really see that. And yeah, thin film wise for us is no issue. It's something that's fully under control if we use it by PCVD or LPCVD. It's something that's for PV cell technology. Yeah, that's mastered currently, so working well.
Then I have one question for you. So for the wet chemical equipment, there are two philosophies: inline and batch. So moving to this larger wafer formats, which one is easy?
This is also a challenging question. I think both applications, even if you would estimate a conveyor transport is easy, you put it on, or on the other hand, you're saying it's easy to have in a carrier wafers there.
Yeah, bigger basket.
Both things, especially as Ryman said, get in that way challenging that we decided for pitches in the carriers for wafer amounts with the automation guys, which right now working, but right now we increasing the area and we having a longer diffusion length. We need to transport bubbles out. We have to carry water cappings. All that is parts of it, as I mentioned. The first part is in the batch system. The other parts are in the jobs to do in the inline system. Definitely, I cannot answer. I would not say it's balanced. Somehow we have to do jobs in both ways, and sometimes things show up. You see downstream later, and our customers come back and say, maybe this is caused by an issue in your machine, what you definitely were not anticipating early on. In general, I agree. If we look on semiconductor, where we're dealing with 300 millimeter wafers, we know what we do. But the difference is here in PV, we want to keep the cost. We want to keep the small footprint. We want to even enlarge the throughput on the same footprint. And this is some streams right now which go into a direction where I definitely will face challenges with Rena. but we managed all these challenges in the past, so I'm very positive that we do this in the future as well.
Okay, I think that's a nice final word. So I think solar has been always challenging for many, many years, in which we all have been active in this industry. But as we've seen, the industry was able to grow, to develop, to increase, improve efficiencies, and with M6 we're actually just mounting another step up the ladder, and we're all confident that this is doable. Thank you so much.
Thank you.